to be able to talk to you about Numba, and I want to assure you I did not slip brown envelopes of cash to Jake before his keynote. He said very, very kind things about Numba that was completely uncoordinated, I swear. And I want to point out I'm speaking on behalf of a whole team of people who work on Numba, and they do amazing work. So, as was mentioned in the keynote, actually, part of the reason that this comes up is because Python is a fantastic glue language. The reason we all use it is because for many of us, the most important resource is developer time. We need to write 3 programs before breakfast to get our research done. And so the best code is easy to understand and easy to modify, but sometimes you need some code to go fast. How many people here have math code they wish went faster? Okay, good. This hopefully will help you. Then what do? And this is where you start to turn to compiler technology to help you out. Now, the reason that a Python compiler is even a possibility is because Python is very dynamic, but in an actual program, most of the time you're only going to call a function with a fairly small number of types. This function could add 2 of anything in the universe, but you're only going to pass 2 floats to it, or something like that. And so that's a point where the overhead of doing compilation is valuable, because then you can specialize, you can generate machine code to manipulate only the types you're using in the program right now. And then in the future, if you switch types, the compilation should switch and use those new types. So the nice part is that implementing a Python compiler has become much easier because the LLVM library, which you may know from Clang that Apple uses now on all of their platforms, already implements a compiler backend. And so all Numba needs to be is the compiler front end. So the Python compilation space is pretty crowded. There's a lot of approaches here, and I don't think that there's necessarily bad duplication of effort here. A lot of people think that we're all in competition here. And really, the space of ways to compile Python is very multidimensional, and I've projected down to here, of whether you do it ahead of time, like something like Python, or just in time, like Numba, and whether you work within the CPython, libpython runtime, like Python and Numba do, or whether you are actually replacing the CPython and libpython runtime like PyPy or Piston would. All of these choices, every one of these boxes has trade-offs, and if your Python compiler project isn't here, I apologize. But we're sitting solidly in that upper right box there because we want to be able to very slightly modify your code. We don't want to cut you off from any of your extensions you're using or any of that. We want you to be able to jump to the function that is the speed bottleneck and improve it, and then not touch the rest of your code. So how Numba works is basically Numba has probably the simplest API you could imagine for a package. It is not quite, but I like to say it's one function. The JIT decorator is the Numba API. And what it does is you just apply the decorator to a function. Let's say we have a function called doMath. Not much happens. We wrap your function in an object that's going to then, when you call it the first time down there in that little interpreter line, when you call doMath, then the machinery starts up. And 2 things happen. We take the actual function body of doMath, and it's bytecodes. So the nice thing about this is that this doesn't care where doMath came from. It could be a lambda, it could be a function you imported, it could be something that you pickled and unpickled with Cloud Pickle. Any of those things are totally legit as long as it's Python bytecode. We run it through a bytecode analysis engine and translate it into a representation that Numba understands. And then at the same time, we take your function arguments, x and y there, and we feed them into the type inference engine. And the point is to say, okay, you called doMath with a float and an int, then we go through the whole rest of your function body and figure out what all the types of all the other variables should be, given those inputs and the operations you do on them. And if we succeed at type inference, and sometimes we don't, because we either don't know about the types you're using or don't know about the functions you're using, but if we do succeed, then we have now the Numba representation has types attached to all those things. Then we can start doing transformations, and right now the rewrite IR pass is really just designed to find where you do an array expression. Say you add some NumPy arrays together. We actually will pull out that expression and do what you call loop fusion, which is to basically say, okay, if I'm going to add these 2 arrays and then multiply by a 3rd array, instead of looping several times for every operation, we combine all those and loop once. So there's a bit of a code transformation there. In the future, we'll be putting more optimizations into that rewrite pass. And then finally, lowering is basically where we emit LLVM IR, which you could think of as kind of like a very portable assembly language. And then feed it into the LLVM JIT. LLVM did all the rest of this chain for us. It takes that, emits some machine code that's in memory. We cache it, so the next time you call doMath with those types, we won't run through this whole compilation process again. We'll just use the one we already saved. That cache doesn't persist between executions, so when you quit your program and come back, we'll have to do the compilation again. But if you call do math with 2 different types, we'll generate a different compiled version and cache it too. So this isn't saying that do math has to only ever work on ints or floats or whatever. We will do the multi-dispatch for you properly. But it's just saying we won't do the compilation more than we have to. And then we'll execute. And you won't notice this, and if you call do math a whole bunch of times, you'll eat this overhead the first time, and then you won't have a whole lot of overhead in the future. So Numba features include, we support Windows, Mac, and Linux, 32 and 64-bit x86 processors, as well as NVIDIA GPUs. I won't have any time to talk about GPU compilation in Numba, but it's a really interesting thing that you should take a look at if you're into GPUs. We support Python 2 and 3, and NumPy versions 1.6 through 1.9. And just to touch on the continuous integration things that were talked about in the previous talks, our Jenkins CI system builds almost every combination of all of these things for every pull request and stuffs them into our anaconda.org build channel. And this is really critical for us. We take this cross-platform compatibility very seriously because we want people to be able to use Numba on any platform they can reasonably run Python on. It does not require, if you are installing this from a Conda, let's say, an already pre-built version of Numba, you don't actually need a C or C++ compiler on your system. So that means that Windows users, where Visual Studio can be quite painful to install, you don't actually have to have Visual Studio. The space requirement's about 70 megabytes. We statically link LLVM. You don't need any of that stuff. And I want to emphasize, we don't replace the Python interpreter. This is a supplement to CPython, not a replacement for it. So you may hear, if you start looking at the Numba documentation or poke around the list, you might hear people starting to use some word jargon. I just want to point out a couple of things. Numba has 2 compilation modes. One of them is called object mode, in which it basically just unrolls the interpreter loop, but still manipulates Python objects. Object mode is not fast. Object mode will run about as fast as the interpreter does. It really exists as a placeholder to allow us to do something called loop lifting, where if you have a loop in the middle of your function that we can compile, we can extract it, compile it silently, and carry on. I won't have time to talk about loop lifting. No Python mode is really the thing most people care about. This means that your compiled function, once you enter into the function, all the Python objects are gone. It's just native machine types all the way down. And we usually find that generated code in no Python mode is within about 25%, as Jake mentioned, of C or Fortran. That 25% really bothers us. Best way to get our attention is to post a blog post about how Numba is slightly slower than your Fortran code, and then we'll obsess over it and try and figure out how to fix it. I'm not kidding. You should see the conversations we have. So how to use Numba? A lot of people think that the first thing you should do to use Numba is to go download Numba, slap JIT on everything, and go home. I'm going to strongly encourage you not to do that. It's more work to do what I'm describing here, but it will benefit you more in the long run. The first thing to do is to have a benchmark. Don't use your unit tests as a benchmark. Your unit tests are seldom a good benchmark. The inputs are too small. Pick some realistic but not running forever kind of way to use your code and say, okay, that's my benchmark, that's what I'm gonna look at. Run a profiler on that benchmark. Something like cprofile is a good choice when you're starting. And look for hotspots. See, oh, this function I call a bunch of times and it eats up 65% of the runtime in my code. If you have 1 or 2 functions like that, Numba is going to be perfect for you because you can zero in on just those functions and not worry about anything else in your code. If those 2 functions are doing a reasonable amount of math and using NumPy arrays, then I think Numba can help you. If you're doing a lot of string manipulation, not today, but maybe in the future, we'll be able to help you. Finally, apply either numba.jit or numba.vectorize. So numba.vectorize is a way to make ufuncs. So if you've seen numpy.vectorize and then ran away because it was really slow when you used it, numba.vectorize is the vectorized decorator you wish you had in NumPy. You'll get a compiled function that's as fast as if you had done it in C. Vectorize I think is underappreciated. Ufuncs are awesome. The broadcast mechanism is awesome. Make more ufuncs and use Numba to do it. And then finally, rerun your benchmark. The point here is to make your code go faster. The point is not to compile code. You can compile things that actually don't run any faster than the NumPy has been optimized quite heavily. So if you're doing a couple of math operations and then you try and use Numba on it, we might not beat NumPy. If that's the case, don't use Numba. You should not add complexity to your code if it's not giving you any speed benefit. So that's why I think that it's really important to complete the cycle. Benchmark, make changes, check your benchmark. All right, I'm going to do a quick sort of whirlwind tour of some Numba features. For those of you who don't necessarily follow the Numba releases, we've been on a 5 or 6 week release cadence since about last year, so we've been pumping out a ton of releases. Part of this is to get versions in your hands so that we can get feedback, and we also have a lot of changes that we're making, and we want to make sure that people see them. So if you looked at Numba a year ago, Numba today is very, very different. So here's the basics. Here's an example function I did. This is a NaN compact. So I have a NumPy array that's got some NaNs in there. I want to get rid of them all. I want a shorter array that only contains the values that are not NaN. Here I just wrote it as a for loop to show you a simple example. The key pieces to note here, the Numba decorator, I passed in no Python equals true. That is not a requirement. We will automatically compile at the highest level we can get away with. What that does is if we can't compile in no Python mode, we'll raise an exception rather than carry on in object mode. So sometimes when you're trying to understand why, whether you're getting the performance you want, you'll put no Python mode equals true in there, just so that you're alerted when we can't compile in no Python mode. One thing to note, which you couldn't do 3 months ago, you can call np.emptyLight. So we have array allocation in no Python mode. This is probably one of the biggest frequently asked features forever. So it's finally there. Here you can see we're looping over that array X that we passed in. We're using an iterator. That's working in here. We understand how to handle iterators of NumPy arrays and tuples and that kind of thing. Here we're using a NumPy math function, np.isNaN. We have basically put into Numba how to compile most NumPy functions. There are some that are missing. The documentation has a reference manual that lists everything we support. And then finally, we're returning a slice of an array. So we've actually done an array allocation, made a slice of it, and we're returning it back to the user. And this is 2.7x speed up over a reasonably compact way you would do it in NumPy. You can call other functions. You can decorate several functions with JIT, and it will, in this case I left off no Python mode equals true, but I can assure you these all compile in no Python mode. And what we do is that we actually give LLVM the information required to decide whether to inline it. So those of you from C compiler land, you know that inlining can be a very powerful tool when you have a simple function to just insert it into the body of your code. LLVM makes the decision whether to inline, so you'll see that I actually inspected the output in order to figure out what was happening here. But the clamp function was inlined. The norm function was sufficiently complicated, it was not inlined. This all happens behind the scenes, but this is one of the many tricks we use to speed things up. And as it happens, this thing for finding the angle between two vectors is about 10x faster than NumPy. I mentioned ufuncs, and you could do some really interesting things with ufuncs that people don't normally do. This is a ufunc that actually runs a Monte Carlo for every element in your array. That's not a traditional way you would use a ufunc, but why not? One of the things to note here is we have no Python mode support for the random number generator. I want to emphasize with bold stars, fireworks, that is not thread safe. So do not write multi-threaded code using the random number generator in NumPy or in Numba. But here I'm using single thread stuff, so it's all cool. So here I have I want a Monte Carlo, basically a tournament structure, which says I'm going to keep playing this game and winning or losing until I either win 12 times or lose 3 times. Those of you who've played Hearthstone probably recognize this tournament structure. And I can run this, and do, basically build my simulation scanning over variables using ufunc, and then, plot the output. So we'll be able to run, 500,000 tournaments in 50 milliseconds. I actually wrote this code because I was trying to figure out why I was failing so much at Hearthstone, why it felt like I constantly sucked. Turns out it's math. So generators, you can write generators that are compiled in no Python mode that you can call from Python or from your no Python functions. So this is another new thing that we only in the last few months has been added. So here I've made a generator that scans complex numbers, scans in the complex plane and emits those. And it's quite a bit faster than doing a similar reasonable thing you might do in NumPy. So if you don't have to give up necessarily all of idiomatic Python. A lot of people complained early Numba felt like Fortran. We're progressing slowly. It was like Fortran 77, then we got to Fortran 90 in March. We're hoping to hit Fortran 2003 by September, and then, sky's the limit from there. And then I saw this on, someone reported me this on Twitter, and so I had to make sure that, yes, you can release the GIL in Numba as well. Obviously, you can only do this on a no Python mode function, but if you pass no GIL equals true, we will release the GIL for you on entry into that function. You don't have to put it on every other sub-function you call, just the one you call into from Python. So, you can, and I would encourage you, as part of Use Python 3, concurrent.futures is awesome. You can get a nice little thread pool executor here. So here's one, me basically using this code here to compute the Mandelbrot set in patches in parallel. And you didn't quite get linear speed up, but it wasn't bad. And I didn't have to go out to a compiled language to do it necessarily. All right, too many things, not enough time, as always. So there are all kinds of things here I couldn't talk about. Couldn't talk about any CUDA pickling functions. You can ship Numba functions to other runtimes through a socket if you want, and it'll just be rejitted on the endpoint and on the wherever. Check the docs. We have extensive documentation of everything we support. You should take a look. What doesn't work, I'm going to really skip this. There's a lot of things. Some things we don't support because they're actually hard to figure out how you would compile them to be efficient. We don't want to support something in Numba that we can't actually speed up for you. Some of these things are definitely on our to-do list, though. JIT classes, I'll just leave as a teaser. A lot of people want to be able to basically take a Python class and use it as a struct in no Python code. That's going to be like September we do that. Bunch of other stuff. So lots of progress in the last year. Try out Numba on your numerical and NumPy related projects. Easiest way to install it is with Conda because we depend on LLVM and compiling LLVM is horrible if you've ever done it. Your feedback makes Numba better. Tell us what you'd like to see. Come to file issues, get on the mailing list, write blog posts, hopefully polite blog posts about things that worked or didn't work for you. We read them and you would be amazed how many things we've inputted just because people asked for them. So, thanks.
So, can you save the LLVM output if you could? Is that a worthwhile thing to do?
Yes, you can. There's a function that basically will dump out the LLVM for a particular type specialization after you've compiled. It's not clear what the value is that in general. Some people actually are trying to use, we have had people use Numba as a way to generate LLVM IR to integrate with a different thing that generates LLVM IR, not Python. And so there have been people who have experimented with using this to embed Python compiled functions they wrote in Python into a different runtime entirely. There's not a big speed advantage. The compilation process is pretty fast on sort of the millisecond to hundreds of microsecond level. So we have investigated whether to cache to disk the compiled versions, in which case we would probably cache the IR because there's issues with caching the machine code and loading in a new installation. I don't know. Is someone back there? Okay. Yeah. Yeah, it's a much, the Python annotate is very, very awesome. I want to give a lot of props to them. That they're sort of our example. Numba annotate is not as far along, but it's the tool in which we want to put those sorts of diagnostics. Right now, what it'll do is if you run your code through Numba annotate, it will emit an HTML file that has color-coded which functions or which loops within those functions were extracted into no Python mode or versus object mode. That's sort of the absolute zeroth layer of kind of debugging you'd want. We want to have more in there. There's also ways to be able to look at things like the generated assembly or the IR if that's important for you as a debugger. But that's the place where we want to do a lot of growth there and really make that the tool that you will use to figure out why is this slow, what can I do, kind of thing. We'll go over there, I guess.
Yeah, how do you deal with the semantic differences between like Python types and C types?
Yeah. So the question is, how do we deal with the semantic difference between Python types and C types? And that's something we wrestle with. In a lot of cases, we defer to NumPy conventions, which are more like C conventions. There are some cases in which there's some tension, and we haven't really resolved it. We actually right now have an internal discussion about how to resolve integer promotion, because it's not obvious what the right way is to do that, given the way Python and NumPy work differently. So it's something we have to resolve on a case-by-case basis, is basically. So we're focused on the numerical users as much as we can. So the convention that benefits them is kind of where we default to for now.
One more question?
Sure, I saw something. Oh, nope. Okay. Oh.
I recall originally the GPU compilation stuff being sort of only the premium version.
Yeah, oh yes, this is something that a lot of people don't realize is actually as of January of last year, the GPU, just the simple GPU compiler is in Numba open source. So you can try it out. You have to write your code as if you were writing a GPU kernel. So if you're familiar with CUDA, it's like that, but in Python. So yeah, it's not a paid feature anymore, it's open sourced.